Welcome to section 3.1, the section on determinants. Recall that for a 2x2 matrix, the determinant is the product of the entries on the main diagonal minus the product of the entries on the non-main diagonal. But what about if your matrix is 3x3 or bigger? So we need a more general formula for finding the determinant. And we're going to get there in steps, and the formula is going to seem a little mysterious at first. First of all, cofactors. The ij cofactor of a matrix is -1 to the I plus j times the determinant of the submatrix you get when you cross out the ith row and the jth column. So let's look at an example where we've got a 3x3 matrix, and let's go through and find three of the cofactors. So C11 is -1 to the 1 plus 1, which is 2, and then I take the determinant of the 2x2 matrix I get by crossing out the first row, first column of A, and that gives me -1. So that's a number. C21, again, same process, except now I'm going to cross out the second row, first column, and my -1 is to the 2 plus 1, which is 3, and so I get -2. Pause the video and see if you can find C31. Okay, hopefully you got -1 to the fourth, and then cross out first column, third row of A, and write down the numbers that are left, 2, 0, -1, 2, and that gives us 4. So note that the -1 to the I plus j is going to form a checkerboard pattern. It's going to go plus, minus, or if you're on the second row, it will start with a minus and then go plus, so on and so forth. Here are the two formulas for cofactor expansion. You can do cofactor expansion down any column or across any row. Don't memorize these formulas, rather memorize the process of finding a determinant. So let's look at an example here. Back to our matrix A. Let's find the determinant using cofactor expansion across the second row. So the step I have written down in front of you is the mental step. Realistically, you're not going to write that down when you're finding determinants. It will take you forever. So realistically, here's what you're going to write down. You're going to write down the determinant is 3 times -1 to the 3, and then subdeterminant 2, 0, 0, 1, plus -1 times 1 times the subdeterminant 1, 0, 2, 1, and finally plus 2 times -1, subdeterminant 1, 2, 2, 0, and then do some computations. This is -3 times 2, so we have -6, and then -1 plus 8, and we get 1. Okay, pause the video and do the same computation. Find a determinant of A, but now do cofactor expansion down the third column. You should still get 1 as your answer, because you can pick any row or any column. All right, I started us out here. We've got 0 times -1 to the 4, and I'm skipping the mental step. I'm going to cross out first row, third column of A, and the numbers that are left are 3, -1, 2, 0, and then I've got 2, -1 to the 5, subdeterminant 1, 2, 2, 0, and then 1 times -1 to the 6, and my subdeterminant will be 1, 2, 3, -1, and that gives us just 0, -2 times -4, plus -7, and again we get 1. Okay, a couple of shortcuts. One isn't really a shortcut. Personally, I detest this method that I'm going to show you because it's gimmicky, it's easy to make a mistake, and it only works for 3x3 matrices. However, the process does have some historical context, so I'm going to include it here. And what you do is, if you're finding the determinant of a 3x3, you copy down the first and second columns again, and then you draw lines going from bottom left to upper right, diagonal lines, and you take negative the product of those entries. Then you draw lines going down, as you can see here, and you take positive the product of those entries, and then you add all those numbers together. So here's an example. We want to find this determinant, and remember, I don't need the word determinant out here because the bars mean determinant. So what I do, here's my solution down here, I copy down first two columns of A, and then I draw arrows going like this. And I take negative the product of those entries. So the first product is already negative. It's -6, so that'll give me a +6. And then I'll subtract. The second product is 0. And then I'll subtract. The third product is 20. And now I'll go down arrows and take those products and leave them whatever sign they are, because I'm taking positive those products. I get 0 plus 0, and then my last product is 16. And so the determinant of A is the sum of all those numbers, 6 minus 20 plus 16, which is 2. Okay, triangular matrices, this is not gimmicky and is incredibly helpful. If you have a triangular matrix, upper or lower, the determinant is the product of the entries on the main diagonal. So in this example here, I've got a 4 by 4. It's triangular, and I can just take the product of those entries to get the determinant. So the determinant is 2 times 3 times negative 2 times 2, which is negative 24. Okay, let's see why this works. Let's do cofactor expansion down the first column repeatedly. So I start with cofactor expansion down this column. Now the only non-zero entry is 2. So I'll have 2, and it's in the positive spot. It's negative 1 to the 1 plus 1. So I didn't even write that down, the negative 1 to the 1 plus 1, because that's positive. And then I write down the subdeterminant that's in yellow. And so I copied that over, and then everything else is 0. Then I do it again, cofactor expansion down the first column. So I have 2, and then I'm going to have 3. Again, it's in the positive spot, times the subdeterminant you see in pink. Everything else is 0. Then the subdeterminant you see in pink is in echelon form. There's a 0 on the bottom left, so its determinant is just the product of the entries on the diagonal. And so you end up with the exact same thing we ended up with before, which is negative 24. So that's very useful. Okay, a couple more topics. Next time we're going to see that if you take the product AB, the determinant of AB is the determinant of A times the determinant of B. Today we're going to see that's true if A is elementary, so we're just going to look at a special case. So first of all, let's look at the determinants of the elementary matrices. Remember, an elementary matrix is a matrix you get from the identity by doing one row operation. So if we scale, let's say row 1 of the identity, we get this matrix here, and its determinant is K. Okay, a swapping elementary matrix gives us determinant negative 1. And a row replacement elementary matrix gives us determinant 1. So that determinant actually doesn't change when you do a row replacement. And these results generalize to any size elementary matrix. Okay, now I'm going to take a generic 2 by 2 matrix A, and note its determinant is AD minus BC, and I'm going to scale row 2 of A by K, and I get this matrix B. Let's write B as the product of an elementary matrix times A. And note, I already took the determinant of B. It's K times the determinant of A. All right, so what elementary matrix would work? Well, I'm going to do the elementary matrix that scales the second row. So 1, 0, 0, K, and then A, B, C, D. If I multiply those two matrices together, I will indeed get B. Let's call this E, and this is A. Note that the determinant of B is indeed the determinant of E, which is K, times the determinant of A. All right, let's look at row replacement. Again, I've taken the matrix A, and in this case, I've replaced row 1 with K, row 2, plus row 1. And I found the determinant of that matrix, and the actual determinant of B is the determinant of A. The determinant did not change when I did a row replacement. So let's write B as the product of the row replacement elementary matrix times A. All right, that would be 1K, 0, 1. And again, note that the determinant of B is the determinant of E, if I call this E, times the determinant of A. So in English, scaling a row of A changes the determinant by that scaling factor K. Row replacement on a matrix A does not change the determinant. And just to speed things along, I've already done these second two examples. Row interchange will change the determinant by a minus sign. And I already wrote B as the product of an elementary matrix E times A. And the more interesting one is number 4. What if you want to scale not just a row, but the whole matrix by a number K? What that does for a 2 by 2 is it's going to change the determinant by K squared. And that generalizes, come down here, if A is n by n and you scale all of A, that will change the determinant by K to the n. Now to justify that, you can't multiply A by a single elementary matrix to scale all of A. You have to do it in steps. E1 would scale row 1 of A, E2 would scale row 2 of A. And so the determinant of B in this case is the determinant of E1, determinant E2, determinant of A. Okay, we'll formalize all this next time, so don't worry too much about memorizing it. Last topic, geometry. The area of a parallelogram spanned by the columns of a 2 by 2 matrix is the absolute value of the determinant. So let's see why that works. We've got a generic matrix A, B, C, D, and it's got 2 columns, and those span a parallelogram. Suppose in the special case that C is 0, then our picture is going to look like this. Now, I've drawn the picture in quadrant 1, but remember, A could be negative, D could be negative, so this parallelogram could lie in any quadrant. Let's look at the area of this parallelogram. It's going to be the base times the height. The base is simply the absolute value of A, and the height is the absolute value of D. Well, that's the absolute value of A times D, which indeed is the absolute value of the determinant of A. All right, well, what if C is not 0? Then you've got a parallelogram that looks something like this. And if I call this angle theta, we can go back to the previous case just by rotating this parallelogram down so that this side does indeed lie on the x-axis. Now, this is the rotation matrix. It's got determinant 1. And we'll see next time that multiplying A by the rotation matrix does not change the determinant. And also, clearly, rotating the parallelogram by an angle of theta is not going to change the area. So that's an interesting result, and it actually generalizes, and we'll talk about that more later. Okay, and that is the end of this section.